In this video, we are going to discuss Gibbs free energy, delta G, and equilibrium, K, and see how these concepts and these quantities are related to one another. So first, we've mentioned how delta G is the main way to predict spontaneity. So what I want to just do is take a minute to summarize how we can predict if a reaction is spontaneous. Okay? So if we have two columns here for spontaneous versus non-spontaneous, we can predict a reaction to be spontaneous using delta G. We learned that a reaction is spontaneous if delta G is less than 0, if it's a negative number. A reaction is non-spontaneous if delta G is greater than 0, if it's positive. So alone, just with the delta G, we can say spontaneous or not. We can also predict spontaneity with K, which we've already actually done. Remember, K is essentially calculated by the products over the reactants, essentially. So spontaneous, in this sense, would mean in the forward direction. So does this reaction favor the products of the reactants? Well, spontaneous means forward direction. So in order for this to favor the forward direction, the value of the products must be greater than the value of the reactants. If this value is greater than the value of the reactants, K is going to be larger than 1. So spontaneous reactions also will have a K value that's greater than 1, and non-spontaneous reactions will have K values that are less than 1. This is the type of thing that I should be able to ask you, boom, right away, and you can tell me spontaneous or not. Delta G less than 0, spontaneous. K less than 1, non-spontaneous. That's got to be rolling off the tongue immediately. But now, how do we relate these two quantities together? Well, there's a simple equation that does so. And that equation says that the Gibbs energy of a reaction, not at equilibrium, not at standard state, is equal to the Gibbs energy of the reaction in the standard state plus RT natural log of Q. So let's break down each one of these values. Again, this is Gibbs that's not at equilibrium. This is Gibbs at standard state, or standard conditions. Okay. R, we haven't reviewed this in a while. This is the ideal gas constant, which, if you check your equation sheet, has multiple numbers listed. It's the same value, but just with different units. The units we're going to use here, since we're dealing with thermodynamics, is going to be 8.314 joules per mole Kelvin. That is the R value that you will always plug in when you're doing a thermodynamic question with R. If you're doing a gas law question, it's a different number. So you've got to be very careful that you're using the right value. T, this is your temperature. What do the units have to be? Well, since the units for R are in Kelvin, the units for temperature also have to be in Kelvin. And finally, natural log of Q. Q is your reaction quotient, okay, which is your products over reactants when you're not at equilibrium. So how do we use that information? Well, let's say you have a problem like so. Calculate delta G, okay, sorry, small little typo, for the reaction below at 298 Kelvin if the pressure of N2, H2, and NH3 are 1 atm, 3 atm, and 0.5 atm respectively. The other information that needs to be given to you is delta G naught is equal to negative 33.3 kilojoules per mole. So I'm trying to solve for delta G, and I'm given delta G naught. So the equation I'm going to need to use that relates those together is delta G equals delta G naught plus RT ln Q. So I'm going to need to know R, T, and Q. So let's figure out what Q is first. Okay? Q is going to be my products over reactants. So I'm given pressure. So there's going to be the pressure of NH3 squared, because of this value here, over pressure of H2 cubed times the pressure of N2 to the power of 1. So if I plug those values in, it's going to be 0.5 squared over 3 cubed times 1 to the power of 1. And if I do the math there, the value comes out to 9.3 times 10 to the negative third. So that's my value of Q. Let's go ahead and plug in my other values that are given to me. Delta G naught, negative 33.3 kilojoules, plus R, note, warning, 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 R is 8.314 joules per mole Kelvin. The problem is delta G is always in kilojoules. So before I plug this in, I need to divide this by 1,000 to convert it to kilojoules. So if I go ahead and do that, divide that by 1,000, same thing as moving the decimal place over 3 times, 0.008314 times the temperature, 298 Kelvin, times the natural log of Q, which is 9.3 times 10 to the negative third. If I go ahead and do the math, I would multiply all these numbers first after getting the natural log. Negative 33 plus those is going to give me a final answer of negative 44.9 kilojoules per mole. Let's pause and think, what does this mean conceptually? This means that since this value is more negative than what it should be at the standard conditions, the reaction is going to shift to get to equilibrium. Okay? Since I basically have too much free energy, this is saying that I favor the reactants too much. So I need to shift to favor the products. So this is going to shift to the right. Okay? If this value had been bigger than delta G naught, that would have shifted to the left. If this value is equal to delta G naught, then you're at equilibrium. So, let's put that together. What if we're at equilibrium? We know that Q is equal to K, and we know that delta G is equal to 0. Okay. So, if I go ahead and plug this value in, my old equation was delta G equals delta G naught plus RT ln Q. So let's plug in our new values now. Delta G is 0. Delta G naught plus RT ln K. So I'm at equilibrium, and I'll put this in orange to make it stand out. So now if we solve for delta G, if we got this by itself, I would subtract RT ln K from both sides. Okay? So what I'm left with is delta G naught is equal to negative RT natural log of K, equilibrium constant. This equation right here is on your equation sheet. So this one you do not have to memorize. The other equation, when you're not at equilibrium, very unlikely that problems like that would occur. We might have to predict how the reaction will shift, but we do need to absolutely know how to use this equation. So let's get some practice doing that now. Calculate delta G for the 3 reactions below. Notice I didn't give you a reaction. All I gave you is K, because that's all you need to know. To get delta G naught, it's always just going to be equal to negative RT ln K. So the only thing that the Gibbs free energy depends on is the temperature of the reaction, and they're all going to be at 298 Kelvin, and what the value of the equilibrium constant is. So for this first one, delta G naught is going to be negative R. Remember, we want to convert it to kilojoules, just out of habit. So it's going to be 0.008314 times 298 times the natural log of 1.5. Natural log of 1.5 first times these values. I get a final answer of -1. Delta G naught is -1. Okay. What about for B? K is equal to 1. So now delta G naught is equal to negative, same thing, 008314, because that's R. T is still the same, natural log of 1. Okay. Natural log of 1 is 0, but you can also check it on your calculator, and you figure out that delta G naught for this reaction is 0. Finally, last but not least, what if K is 0.67? Now delta G naught is equal to negative 0.008314 times 298 times natural log of 0.67. You go ahead and do the math here. You see that delta G naught is equal to 1. Final answer. So let's pause and think. What's the importance of this? Well, we said at the beginning, a reaction is spontaneous if delta G naught is less than 0 and K is greater than 1. Let's see here. Where do we have delta G less than 0 and K greater than 1? Delta G less than 0, K greater than 1. Those agree. Those always have to be true. This is spontaneous in the forward direction. What about non-spontaneous? Okay. Non-spontaneous when delta G is greater than 0 and K is less than 1. So when does that happen? Does that agree with what we would predict? Delta G greater than 0, K less than 1. This agrees. Non-spontaneous. Okay? So what we're seeing is that that actually totally agrees with what we would expect to predict spontaneity. Key points to walk away from today. Units. You've got to be careful. With R, they're in joules per mole Kelvin. So you need to convert to kilojoules. Watch out for that conversion. Don't forget to make that conversion to kilojoules. Equilibrium. Okay? Equilibrium has a different equation. The equilibrium equation is the one that you need to be more familiar with, and this is what's on the equation sheet when we use K in this equation instead. Last but not least, the ideal gas constant, R, is 8.314 joules per mole Kelvin. It's also equal to 0.08206, but that has units of liter atmospheres per mole Kelvin. So these are the same values, same number, but just with different units. This is what we need to use for all our thermodynamic calculations involving R. And now we have put together Gibbs free energy and equilibrium.